So, a very good morning to you all. In today's lecture, I will be discussing about electromagnetic potentials from a moving charge, and they are known as Lienard-Wiechert potential. So, as I told you in the last lecture, that if a charge is moving, so we can call that as a source, and the observation is made at a point, we call it as a field point. So the information generated by the source when it reaches at the field point, in the meantime, the charge moves from its position to another forward position, and therefore, in the present position, the information which is received by the observer at the field point is related with the earlier time, and we call it as a retarded time. So Lienard-Wiechert potential are nothing but the scalar and vector potential produced by a moving charge. So as I told you in the last lecture, that there are two ways, either the method of retardation or the method of special theory of relativity. We can have either of the two to understand these potentials. So I am making use of basically the Lienard-Wiechert potential, because Lienard and Wiechert basically made use of retarded potentials to find out the expression for A and B by solving the two inhomogeneous equation. So the two inhomogeneous equations are del square minus 1 over C square, del square over del T square into A is equal to minus mu 0 J, or D L inversion square A is equal to minus mu 0 J, and D L inversion square B is minus rho upon epsilon 0. So these are basically the two equations obtained after applying the Lorentz gauge condition, and both the equations can be solved on the same footing. So we have basically a volume charge. So here this Q represents a volume charge. It is made up of several charges together. So we have a volume charge that is moving with a velocity v along an arbitrary path shown like this, with a velocity to be equal to v. The source here is basically Q, and the field point, the point of observation, is P. We have basically a coordinate system whose origin here is O. And with reference to the origin of the coordinate system, the coordinates of field point is R, that is fixed, and T is the time of observation. So at time when the observation is made by the observer at the field point, the information that was generated by the charge here, because it will take a time, if this distance is equal to R, here Q is the retarded position. I will explain why we call it as a retarded position. The position coordinate of this charge Q at that instant is R dash, and R dash is a function of basically this T dash here. The information from generated, the electromagnetic field generated by the charge Q takes a time T to reach, basically it takes a time R by C. C is the velocity of light, velocity of propagation of electromagnetic waves. So R by C is the time taken by this electromagnetic signal to reach the field point. And if the observation is made by the observer at time T, that means whatever he is getting here at the field point must have been generated at R by C time earlier, or at a time T minus R by C, and the time T minus R by C here is basically T dash, and that is called a retarded time. So P is a field point with respect to O. The position coordinate are R and T as a function of, in fact, R and T are not going to change, because R is the point of observation, that is fixed forever. T is the time of observation, that is also fixed. The charge is moving. So the moment this electromagnetic signal starts coming from here, and when this field point or observer at the field point receives the signal, the charge might have reached at some a position here, and the position vector will become now r plus dr. It will not be equal to r. That is what you have to realize. Now, if you look at here, the retarded position q, position vector is r dash t. R is the position vector of basically q at the field point or at the point of observation, and the position vector of field point with reference to O is r. So if you make a use of this triangle, we can write down vector r dash plus vector r is equal to r. Our capital R is nothing but r minus r dash. In fact, we can write these points as x, y, z are x dash, y dash, and z dash, and in that case, the value of r will be equal to I cap into x plus j cap into y plus k cap into z, and similarly r dash will become I cap into x dash, j cap plus j cap into y dash, and k cap into z dash. So now we have to solve. If you look at these two equations, these equations are similar to basically the Poisson equation. In case of Poisson equation, we did not have the time coordinate here, that 1 upon c square del square over del square t square was not there, and we had the equation del square v is equal to minus rho upon epsilon 0, and I told you how to write down the solution of Poisson equation. We wrote the solution v as a function of r, and the time t was equal to 1 upon 4 pi epsilon 0 integration over the whole volume rho into d tau divided by r. So on the similar footing, in fact, it's a 4-dimensional problem. It's a problem of electrodynamics where time variation has also been taken into consideration. So if this distribution of charge in the volume is defined by, let us say, j and rho again, so we can write down the solution of these two equations here as a VRT, V at position R and time t is 1 upon 4 pi epsilon 0 rho at R dash, and at time t minus R upon C divided by R into d tau. So the only difference in the equation wrote yesterday, or the solution wrote yesterday, and here we are taking R dash, and R dash is changing as a function of time, and then t minus R over C, because the present position and the position when the electromagnetic signal was generated by the charge are different. So the signal received at time t was generated by the charge at r by c earlier, where r is the position coordinate of the retarded position of the charge. So we can write it like this. This is d tau, and it's a volume integral. Similarly, we can solve this equation also. This equation ART can be written as mu 0 upon 4 pi, and then j r dash again at t minus r over c divided by r into d tau, because the two equations are the same. Only difference is that here we have mu 0 upon 4 pi. Some people will write it as 1 upon 4 pi epsilon 0 also, but if you multiply both the numerator and denominator by epsilon 0, then you will have 1 upon 4 pi epsilon 0 c square, because mu naught epsilon naught is 1 over c square. So r by c here, if you look at these two integrals cannot be solved as it is, because r by c here is different for different constituents charge of the volume, because the volume charge is made up of several charges together, and the value of r over c is different for different constituent charges of which this volume element is made up of. Therefore, the additional integration over the source time t dash together with the volume integration tau has to be performed. Then only we can get the electromagnetic field potential, that is A and B. So what do we do this for? To account basically, or to consider the contribution from T dash also, we take the help of Dirac delta function. Now at this stage, there are several ways of doing it, but mathematically, the method of using Dirac delta function is relatively easier. So that is why I am going to discuss with you the way of solving these two integrals exploiting the property of delta function. So first I will write down the four property of delta function. You all know basically the delta function very well. You must have read it in mathematical physics last year. The first is delta at x is equal to 0 is 0. If it is 0, only if this x is non-zero. Delta at x is equal to 0 is non-zero. Delta at x is equal to 0 is non-zero, but delta at x is 0 for x to be equal to non-zero. So you have to understand. The other is minus infinity to infinity, delta x dx is equal to 1. That is another very important property of Dirac delta function. I am writing basically those two properties again here so that they are there on this page also. The third property is if you multiply a function fx by a delta function fx delta of x minus a, then x is equal to a is replaced and we get f of a at delta x minus a. And then I integral minus infinity to plus infinity, f of x delta of x minus x dx is equal to f of a. So all these properties are very much familiar to all of you because they are very simple properties of a Dirac delta function. So by making use of these properties, the first one and the second one here, we modify now this VRT and ART. You see here, this integral, the volume integral over the tau, tau is the representation for the volume. We are introducing minus infinity to infinity. So it's minus infinity to infinity. Delta here, delta of t dash minus t minus r over c, because t is equal to basically t minus t over c. So this is equal to 0. So delta of 0 is not equal to 0. So that is why this function is not equal to 0 has been written here. So delta of 0 is not equal to 0. So that is why we have delta 0 here. And then minus infinity to infinity, delta of x into dx is equal to 1. So the variable here is t dash. So we have dt dash here. Same thing has been done to basically write a also. ART is mu 0 upon 4 pi. Again the integration over the volume. Now integration over the time between the limits minus infinity to plus infinity. J dash r dash t dash and then delta of t dash minus t minus r over c d tau dt dash divided by r. So we have basically inserted a delta function into it without changing the equation. So now it has a double integral. Now if you look at this equation, rho at r dash t dash. What is rho? Rho is the volume charge density. And what is d tau? D tau is the volume. So rho at r dash and t dash into d tau is dq. It is the charge in the volume element d tau. So if we integrate it over the whole volume, we can approximate it to basically the total charge enclosed within the volume under consideration, that is moving with a velocity v. So we will write this. So anyway, this is equal to dq, and then we will replace it by q also. Similarly, J here is equal to rho into v. The charge density, the current density is defined as the product of volume charge density and the velocity. So J into d tau becomes a rho at the same time, and the position multiplied by v, the velocity of the charge at the same time t dash and d tau. Rho and d tau together will give us again the charge contained by the volume element d tau. So this becomes a v at t dash divided by dq. V at t dash is nothing but the velocity of the charge at that point when the electromagnetic signal was generated at the source point and received at the field point. So we have made use of the same thing in place of a rho into rho at r dash t dash into d tau. The dq has been replaced. Now look at this. If integration over tau into dq, integration over the whole volume dq is the total charge contained by the volume element under consideration, then we can remove this integral dq and write at q, and then we are left with basically a time integral that we changed by using the Dirac delta function. So with this way, we can write down VRT, Q will come out. So Q upon 4 pi epsilon 0, now minus infinity to plus infinity. And then delta function of this quantity into dt dash divided by capital R here. Capital R is nothing but the mod of vector R. We have to be very careful while defining the mod of a vector R and the vector R, because that might confuse us at several places in the coming lecture as well as this lecture also. So we have to be careful. It's a magnitude of R, so that is why there is no vector. Now in order to solve this integral, this is now volume, both the integrals are going in the same way. We have basically the velocity term here, that is additional, and we have mu 0 upon 4 pi, and here we have 1 upon 4 pi epsilon 0. So we assume that this quantity in here, the delta function, t dash minus t plus t over rc is equal to t double dash. Although this is equal to 0, but since delta function is not equal to 0, so we are going to apply mathematics on it. So we assume this to be another new variable, that is t double dash. So t double dash is a new variable. So we now differentiate this. So dt double dash is now dt dash, but dt is equal to 0 because the observation is made at the fixed time and also at the fixed position. The field point, the point of observation is fixed, R is fixed, and t is also fixed. That is why the value of a dt will be equal to 0 because observation is made at the fixed time. So, but this now, this dr, I have written 1 over c as it is. I have written it as dr over dt multiplied by dt dash, so that we could calculate the value of a dr over dt. So if you look at r now, vector of r is r vector r minus r dash. We can, in vector form, we can write it as I cap into x minus x dash plus j cap into y minus y dash plus k cap into z minus z dash. So this r now becomes equal to square root of x minus x dash whole square plus y minus y dash whole square plus z minus z dash whole square. Now differentiate this with respect to t dash. If you differentiate this whole to the power of half, so x to the power half after differentiation gives us 1 upon 2, then x to the power of half minus 1, so that becomes minus half. So square root of this will come into the denominator, and I have written it to be equal to r. So this is 1 over 2r, and then the differentiation of whatever is written inside the square root. So we differentiate it again. When we will differentiate all these terms, 2 factor will also come. So I have taken 2 out. Then x minus x dash, and the differentiation of now x minus x dash. The differentiation of x will be equal to 0. As I told you, that point of observation is fixed. So any change in x is not allowed. Same argument holds for y and z also, because its coordinate is x, y, z. So this becomes x minus x dash minus dx dash upon dt dash, y minus y dash minus dy dash over dt dash, and z minus z dash into minus dz dash over dt dash. 2 will cancel out and we are left with 1 over r. We take out the minus sign from the whole bracket, and then whatever we are left inside the bracket can be written as r dot b. R dot b, r is I cap x minus x dash plus j cap y minus y dash plus k cap into z minus z dash. Dx dash upon dt dash is basically the rate of change of x coordinate of the charge when the electromagnetic signal was generated with reference to the time at which it was generated. Same thing for dy dash over dt dash and dz dash over dt dash. So v dash, v is the retarded velocity or the velocity when the signal was generated. So we can write dr over dt dash to be equal to minus 1 over r, and then r over v with a minus sign. Now we go back to our equation. We substitute it here. So if you substitute, dt double dash is now equal to dt dash minus 1 over rc r dot b into dt, and if you take out dt dash common, then and I have written here r vector over r as r cap unit vector r. So it becomes 1 minus r cap dot b over c. You can dimensionally also verify, because 1 is a dimensionless quantity. Here we have r cap, that is a unit vector. B by c is basically a dimensionless quantity, because we have velocity and the velocity of light in the denominator. So this gives us the value of a dt dash to be equal to this dt double dash divided by this 1 minus r cap dot b over c. So now we substitute it in the value of v and a expressions. So once we get these expressions, we get it something like this. Now we make use of the fourth property of our Dirac delta function. What is the property? That whatever appears along with the delta function, delta of x minus a. So if we put x minus a to be equal to 0 in the function, then we can evaluate this integral. So here q upon 4 pi epsilon 0 will remain as it is. What is the function? The function is 1 over r, and inside the bracket we have 1 minus r dot b over c. This at t double dash to be equal to 0. X minus a to be equal to 0 means x is equal to a. Here we have taken t double dash to be equal to 0. So t double dash to be equal to 0 means the value of this function at a t dash to be equal to t minus r over c. Same thing we have to do for a also. Here again the function is different. So b upon this function evaluated at t dash to be equal to t minus r over c. So what is t dash? T dash is basically a time r by c times earlier than the observation made by the observer at the field point. So we call it as a retarded time. And since the expression for v and a, the field, the vector potential and the scalar potential, they have a relation with the retarded position, because unless and until we calculate the value of this function at a retarded position, we will not be able to evaluate this. So these potentials are also called a retarded potential, and these are also called Lienard Wiechert potential, because Lienard Wiechert basically are the one who basically derived them in terms of the retarded potential. So it must be clear why they are called retarded potential, and we call them as a Lienard Wiechert potential. Now if you look at the expression for B, if you compare it in case of electrostatics, we found that V was equal to Q upon 4 pi epsilon 0 1 over R. You have a charge, the potential at a position R due to a point charge is given by 1 upon 4 pi epsilon 0 Q over R. But you see here the entire thing is modified by a factor 1 upon 1 minus R cap dot V over C. So in fact, we can visualize these expressions from the relativistic point of view. If you make use of the relativistic dynamics, that means the theory of relativity. So this is basically a correction function. If you read a book by Griffith, you will find out how this function appears because of the relativistic correction. So I will not go into the details, but you can have an understanding that these expressions for electromagnetic vector potential and the scalar potential, both of them gets modified by a factor 1 minus R cap dot V over C to the power of -1, because it is in the denominator, and this entire function has to be evaluated at the retarded position. Now, suppose we want to write down the relationship between the two. You divide one by other. You divide A by B. So let us calculate A by B. Here we will be left with A by B. We will be left with mu 0. What we do, we multiply this here. I have written epsilon 0 extra. So please ignore it. If you write down epsilon 0 here, write down epsilon 0 here also. So let us include 1 epsilon 0 here also, and then we divide A by B. So we are left with mu 0, epsilon 0 and B. All other terms will cancel. So if you look at the expression here. Both the expressions are written here. If you divide, then V upon A upon V, that is what is had is written. A at R and T, A at the field position is equal to mu 0 epsilon 0 V into V at the position R and T. So mu 0 epsilon 0 is 1 over C square, and therefore we can write this A as B upon C square into B. So the two are interrelated with each other. So this is all about Lienard potential. Now I am going to solve two problems. In fact, I have two problems for today's lecture, but let us see if the time will permit, then I will discuss both the problems in today's lecture. Otherwise, I will discuss one problem at least in today's lecture. The first problem is the calculation of gradient of TR. TR is nothing but a retarded time. TR and T dash. So now I will make use of TR to represent the retarded time. What is TR? TR here is a T minus R over C. This is the retarded time you can see. So if you play with this equation, we can write down R to be equal to C into T minus TR here. So T minus TR here, and similarly vector R can be written as R vector minus R dash vector. So be careful now with R and R vector. So we make use of this equation. R is equal to C into T minus TR. So in order to calculate gradient of TR, we take gradient of both sides. So if you take the gradient of right hand side, so gradient of T will be equal to 0 because that is the field point. So minus a C into gradient of R will become gradient of now R mod or magnitude. This R mod can be written as the square root of R dot R, because if you expand R dot R is R vector into the mod of R vector, the mod of R vector into the cosine of the angle between the two, that is 0. So it becomes R square. So we can write it as square root of R dot R. If you differentiate, because this gradient is nothing but a differentiation, so if you differentiate, half will come, and then this whole to the power of minus half will come. That is why I have written under root of R dot R, or under root of simply R square. So that gives us R in the denominator. Then it becomes now the gradient of R dot R. We made use of identity, Griffith identity number 4. So that identity number 4 will help us to write this gradient of A dot B formula. Here we have R dot R. So gradient of R dot R will have 4 terms. But if A and B are the same, then the first two and the last two terms are the same. So a factor of 2 will come here. And then we have R dot del into R plus R cross del cross R. And that is the value of minus C into gradient of TR. Let us now calculate the values one by one. So R dot del, see now here, I am calculating now the value of R dot del R here. So this is now vector R. So vector R is now small r vector minus small r dash vector. So I write it R dot del as it is. So it is R dot del, then vector R minus R dot del into R dash. This R dot del into R I have written as capital R vector, but please calculate it. If you expand it, so this becomes Rx into del over del x plus Ry into del over del y plus Rz into del over del z. If you perform the operation del over del x of R vector R, so x will differentiate and give us to be equal to 1. So we will be left with I cap. So I cap into Rx plus j cap into Ry plus k cap into Rz will give us this vector R. So it's very easy to calculate, but please calculate for the first time so that you can visualize next time to write this R dot del into R to be equal to R. Now I move on to the other one. Here this Rx into del R dash, or maybe you can understand it from here. Suppose it is R here. So delta r will become I cap into del r, I cap into del x plus j cap into del y plus k cap into del z. So here you will get I cap, here you will get j cap, here you will get k cap for this. That is why it is r. But here this is del r dash over del x, del r dash over del y, and del r dash to be del z. But to make this reasonable, we write it as a del r dash over del tr into del tr over del x. Same thing we do basically for the remaining two terms also. Now we take a del r dash over del tr common. What is del r dash over del tr? R dash is the retarded position of the charge and tr is the retarded time. So rate of change of position coordinate with reference to the time is the velocity of the particle. So the velocity of the particle at that instant is a v, and then we are left with rx into del tr over del x plus ry into del tr over del y plus rz into del tr over del z, and these three terms together can be written as r dot gradient of tr. R dot gradient of tr. Gradient of tr will become I cap del tr over del x plus j cap del tr over del y plus k cap del tr over del z. And therefore we can write this r minus v into r dot gradient of tr, the first term. Let us now calculate this curl of r. So curl of r can be again written as curl of r here can be written as curl of small r minus curl of r dash. So I have written the value of curl of r to be equal to 0 plus please calculate yourself. You have to write down a determinant like this. You will have x here, y here and z here. Verify yourself that the curl of r will come out to be equal to 0. So I have written curl of r dash, so I, j, k, and then del over del x, del over del y, del over del z coming from del, and r dash components are x dash, y dash, and z dash. I have written only one component, that is why I have made use of the summation. That means we can write down the similar three terms, similar to other terms for y and z coordinates also. So for I cap, it is a del z cap over del y minus del y dash over del z. What we have to do here again, similar to this, we have to write this as del z dash over del tr and then del tr over del y. Similarly here, del y dash over del tr and del tr over del z. Why are we doing this? Because by doing this, we have basically now a reasonable velocity component here, because this delta del z dash over del tr is nothing but the z component of the velocity at the retarded position. Similarly, this is the y component of the velocity at the retarded position. So this entire thing can be written as v cross gradient of tr. So what I have done, I have made use of the first term here to write down this v cross tr. So you check I, j, k will appear. V is del x dash over del tr, del y dash over del tr, and del z dash over del tr, and gradient of tr components will become del tr over del x, del tr over del y, and del tr over del z. So you can see these components here. So we have v cross del tr. Now if you expand it, so we are getting I cap into del y dash, this term. So this minus sign will go inside, and then only this becomes basically the x component or the coefficient of I cap of v cross gradient of tr. So please verify at your end also that this curl of r becomes v cross gradient of tr. Now we move to the original equation and we substitute all these values that we have calculated. So you see here, on the left hand side, we had minus c into gradient of tr. It is 1 over r. The first term that we calculated was equal to vector r minus the velocity vector. And inside the bracket, we had r dot gradient of tr, that is a scalar quantity, plus r cross, we had basically del cross r, and del cross r is now v cross gradient of r. So that we have written here. Now, I wrote another formula A cross B cross C and requested you all basically to remember it as BAC minus CAB formula. So this is A cross B cross C. It is B inside the bracket A dot C and then CAB, C inside the bracket A dot B. So this is A, this is B, and this is C. So BAC. So in place of B, we will have the velocity vector, and then R dot gradient of TR minus sign will appear. Then CAB in place of C, we have gradient of TR and then R dot B. So you see now the third term is similar to the second term, so they cancel out, and we are left with now R cap minus gradient of TR and R dot B. So now with a little rearrangement, because we have gradient of TR here, so we take it onto this side and we can rearrange this to write down gradient of TR to be equal to minus vector R upon RC minus RB. It's a very important expression that will be very useful in the next lecture while getting the information about the electric field vector E and the magnetic field vector B from the Lineart Wiechert potential. Similarly, I will solve now the second problem also. The second problem is to find out here we calculated the spatial derivative of the retarded time. Now next is to solve for finding out del TR over del T. That means the rate of change of retarded time with reference to T. T is the time of observation. So now in order to calculate this, what we will do now, we again make use of the equation R to be equal to C into R T minus TR. We differentiate this. So we have del R over del T. It is now equal to C into 1 minus the differentiation of T is 1 with reference to T dr we are differentiating. And this becomes now del TR over del T. This we will write as a del R over del TR and then del TR over del T. And this becomes now C into 1 minus RC. We multiply it by C. So it is C minus C into del TR over del T. So this is simple. If we calculate the value of this del R over del TR here, we will substitute it here and find out the value of del TR over del T. So let us now apply. These are basically the two very important problems given in Griffith. The second problem is basically unsolved in Griffith and the first one is solved there. So you can check basically both the problems there. So here again I am writing R as square root of R dot R vector. So R dot R vector is R square root will give us mod of R. So del R we differentiate now with reference to TR again. So del R over del TR. So del R over del TR is now equal to 1 over 2R, 1 over 2, which it will come because of power half, and then R will come in the denominator. Now we differentiate inside. So it is R dot del R over del TR plus del R over del TR dot R. A dot B is B dot A, we all know. So therefore, the first term here and the second term are the same. So we can write them as twice of this. But I have written a minus sign. You can see a minus sign here. Why the minus sign is appearing here? This del R over del TR. What is R? Vector R is basically vector R, small r minus small r dash. So if you differentiate with reference to TR, the R will not change because R is the position vector of the point of observation. Basically, it is the R dash which is changing with TR defines the velocity of the particle. So that is why this V is minus, V is del R dash over del TR. So that is why we have a minus sign here. So 2 and 2 will cancel and we have basically minus R cap again. Why? Because we have a vector R here. Vector R divided by R becomes R cap and we can prove it del R over del TR to be equal to minus R cap dot B. You will have to remember even del R over del TR to be equal to minus R dot B. That we will also be using in the next lecture. So let us now substitute these values here. So if you substitute the value here, then we get the value of del TR over del T to be equal to C upon C minus unit vector R dot B. Again, if we write this unit vector R as vector R divided by the mod of R, that is R, then this becomes now vector R divided by R. So now we can multiply both the numerator and denominator by capital R and write it in this form. Del T R over del T is equal to RC upon RC minus R dot B. In most of the situations, we will be using it like this. That is why we are writing it in this form. Now let us define a vector U. This will also come in the next lecture. We will define a vector U. U is a C R cap. R cap is R over R and minus B. If we define this U and take the dot product of R with U, you see R dot R becomes R square divided by R will make us R. So we have RC. It's a scalar quantity because the dot product is a scalar quantity. And this is R dot B. So RC minus R dot B in terms of a U can be written as R dot U also. So you can see here that we can write this del TR over del T to be equal to RC minus R dot U. Similarly, we can also write even gradient of TR that we solved as a problem number 1. And here also we can write this as gradient of TR to be equal to minus vector R divided by U, because the denominator is written in terms of U. So we will be using this U also. So this is all about basically the today's lecture. So in today's lecture, I have calculated the expression for A and B. Since they are expressed in terms of the retarded time, they are called retarded potentials or retarded electromagnetic potentials, retarded vector potential and the scalar potentials. They are also called Lineart Wiechert potential. And then we will have to write down the E and B because we cannot understand these results in the present form. So we will now write down, we will derive basically the electric field and the magnetic field by using these Lineart Wiechert potential. And in that, we will need basically gradient of a TR and the time derivative of a TR. So that is why I have derived both of them as a problem in this lecture. So I will stop here today, and in the next lecture we will make use of these expressions and these two problems a solution to basically solve for E and B for a moving charge. Thank you. So that is all for today.